Okay, so here's a continuation of class 3, and we're going to talk about pressure gauges and measuring of pressures. So first, that gauge that you're used to when you think of a pressure gauge is another name for it is a board-on tube gauge. And the most general type of construction of it is to have this a cut-off circular type of tube right here that they're calling the board-on tube. And you can kind of picture how it's going to try to elongate with higher pressure. And that elongation can be geared to a needle. And if we have it set up the right way and calibrated, we'll be able to measure what the pressure is based on the elongation, of course. And remember, for mechanics and materials, that's going to be this cross section, and the material stiffness is going to really determine how this thing behaves. So you can kind of appreciate how these can get out of whack over time. Maybe the material, it gets over pressurized, and maybe this thing gets have a high stress and maybe go past its elastic limit. But also just with corrosion and other things could affect how this needle behaves. And it also can get restricted by way of vacuum. So it could go a lot of gauges are both a pressure and a vacuum, so they're balanced in between. And noteworthy, I don't know if you can read this, you'll see a lot of times on the pressure side of it, it'll be like PSIG, right? But below 0, it won't be negative numbers. We'll say this is inches mercury, and this a lot of times we'll write VACs for vacuum. Will be in on there. And you can think of the board-on tube being a lot like that little party favor type of thing. I don't even know what you want to call that thing, but maybe we should bring those in class so that we can all have them and communicate by party favors. Here's a little close-up. Here's a better close-up. All right, so that's better because I just said, hey, I wish you could see that. But here's PSIG for on the positive pressure side, and you can see here's inches mercury on the vacuum side of it. And if you're calibrated correctly, when there's no pressure on there, it should be at 0 when we're at atmospheric pressure. And you can kind of see the internals, and this is not what all of them look like, but this particular one does. You can see there's means of trying to make little micro adjustments for calibration. And this one looks like it might actually be a combination mechanical and maybe even be able to put out an electrical signal as well. Another way that you could communicate a pressure is to have this right here. We might think of this as a barometer, right? So this is a very simple barometer. You could have any liquid in there, but mercury is a preferred one because you see this little diagram in the middle. This is out of Munson's book. If you were to use water instead to measure atmospheric pressure, like right here, this is how tall it would be. And so like the idea of creating this would be kind of pretty nasty to make one that would a barometer that would look exactly like this. This isn't really what they look like, but maybe if you were to invent your own one, what you could do is you take this clean tube and maybe immerse it inside the mercury so that all the air is gone, and then you would lift it up vertically and very carefully, not to get mercury poisoning. And as you would lift it up, this vapor inside right here, this would be mercury vapor. And so this height right here would be a means of measuring what the atmospheric pressure would be, right? You presume that this vapor pressure is very, very, very small, so we could assume that it's going to be 0, and so like the height of this thing is what the atmospheric pressure is pushing back up onto the thing. And so if the tubes aren't so small that they would create some capillary action, because remember when we talked about surface tension, or if you remember that video, we can have capillary action going here, but if the area is not too small, and so surface tension is not causing capillary action, irregardless of the diameter of the tube or how tall the tube is, this height would remain the same for a given atmospheric pressure. We also have, and this is not in our notes, but we would also have various types of transducers that will produce a signal that a digital gauge board would be able to pick up. And of course, that's more of the modern trend than having those bird-on tubes. So most of the time, though, they'll be redundant in systems where you'll have both the electronic one, but there's also a means of measuring it locally, because something could go wrong in the circuit and that type of thing. And also, some of these might need to be replaced over time. They all come with calibration stickers and that kind of thing, but it's really good. It would be necessary to calibrate them periodically. So this is the source, by the way, of, you can go to this website and read some more about these gauges. I think I need to switch over to my, let's see, over to my notes and things that we want to bring up. And we already mentioned this before, but when we give it pressure in PSI-A, that's like the PSI-G, what we read on the gauge, plus the atmospheric pressure, right? That's the so that's the nomenclature that we want to try to remember and maintain. And we have the atmospheric pressure is standard 14.7 psi, or 101. Sometimes 101.4 kilopascals that we typically want to look at. And here's that description, very simple barometer. Note how very small the vapor pressure is of mercury, right? So vapor pressure of mercury is 0.000, I lost track. That's how many zeros there are, 2-3 psi-A. So small that we could say that the if we want to find the atmospheric pressure, we could take the density of mercury as a liquid mercury times its height, this H right there. And that would be what we define as the atmospheric pressure. So quite often we are measuring, as we noted in the gauge up above, inches of mercury is the means to measure vacuum, right? Going the other direction. And remember that we're going, it starts to get negative, right? So we would say this right here would be 10 inches of mercury VAC, and what we know is that that's going to be below atmospheric pressure, and so that means vacuum that we would put. So I have a calculation right here. So standard atmosphere, PATM, is 14.7 pounds per square inch, right? Well, let's turn that into 144 inches squared per foot squared, and divide that by the density of the weight density of mercury, which is 847 pounds per cubic foot. And what we're left with is we have 2.499 feet of mercury, but a lot of times we'll use inches of mercury in US units. So that comes out to 29.99 inches of mercury. Now, 14.7 is sort of a round off thing. Absolute vacuum is actually 29.92 inches of mercury is standard atmospheric pressure. And therefore, if we were talking about how much vacuum is possible, this is the most amount of vacuum that is possible, is 29.92 inches of mercury. If you want to take a look at standard SI here, we could do the same thing and take 101 kilopascals and divide it by 133 kilonewtons per meter squared, and you're going to end up with 0.7594 meters of mercury, which is going to be 759.4 millimeters of mercury. Just to give you sort of an idea. So in SI units, a lot of times for vacuum, we might, just as a practical matter, use millimeters of mercury. So you have something to compare it to right in there. let's see, do we want to go to the next thing? Let's make that a separate video. All right, so this is end of video 3. And I think I'll call that pressure measurement devices.